So this next set of questions, you have the boulder has a mass of 30 kilograms, and it's on a cliff that's 18 meters high. It's traveling at 20 meters per second and going to go off into the air. So it's going to go off into the air like that. So let's write down some of your variables. This is launched horizontally. So this is v sub 0. It's also v sub 0 x because v sub 0 y is 0, right? It's launched. That is such physics jargon, but all we're saying is that we threw it horizontally. You didn't throw it upwards or downwards when it left your hand. So that's why that's 0. It has no initial up and down speed. It just has sideways speed. So its initial velocity is all sideways. That's the x part, is all sideways. And it's 20. So that it's all 20. None of it's up and down. Well, it's 20 meters, it's 18 meters high, which means that delta y is going to be negative 18 meters because it's going to fall downwards. We're going to need to find its range, which is your delta x or r. All right, again, you can use a delta x or an r. You have no acceleration in these things, no acceleration in the x-axis. We're ignoring air resistance for all these things. But you do have acceleration on the y-axis, and the acceleration on the y-axis is negative g. Okay, so the acceleration on the y-axis is negative g. Sorry, in the x-axis, there isn't any. So we always solve for time. We don't always, but we typically solve for time, which is question 15. In the y-axis, because we have enough information for that. We know its acceleration in the y-axis, we know its initial velocity in the y-axis, and we know its displacement in the y-axis, so I can solve for time. How long will it take to reach the ground? By the way, we do not know its final velocity in the y-axis. You can solve for it, but it's not 0. The final velocity in the y-axis isn't 0, because as long as you're using an acceleration of negative 9.8 or negative 10 meters per second squared, it's still falling. Yeah, it's going to come to 0 at some point, but not with that acceleration. You can only use these equations as long as the acceleration stays the same throughout the entire problem. That's why we don't know the final velocity as it's falling through the air. But you could calculate it, but you don't need to. At least, no, you don't need to. So for question 15, how long will it take? Well, that's going to be t, obviously. So delta y equals the initial velocity in the y-axis, not the x, don't use the 20, use 0 times t, plus 1/2 of the acceleration in the y-axis, because then everything's y, times time squared. This is 0. 0 times anything is 0. This is negative 18 equals 0 plus 1/2 times negative 10 times t squared. So you solve for t squared, and then you take the square root to get t. And let me see here. That's going to be... Somebody's coming. Okay. I'm back. So where were we? Oh, that's right. We were calculating this. I get that t squared is equal to, what did I get? I don't know, 3.6. So that's 3.6. Take the square root of that is about 1.9. Is that what I got on this? Question 15. Yeah, 1.9 seconds. Good. So it's going to take 1.9 seconds to fall. That's the answer to part 15. How far from the base of the cliff does it land, i.e. what's its range? Okay, I'm going to erase this. Remember the 1.9. So question 16, what's the range? Delta x, again this is question 16. A lot of students, a lot of you incorrectly use this equation. You can, but most people use it incorrectly. I would not use this here. And let me. So I'm going to go back and do this a different way. That actually does work, but most people incorrectly use it. The reason why they incorrectly use it is v sub 0x is 20, but then folks have this habit of putting 0 right here. It's not 0, it's 20 also. 20 plus 20 is 40, and half of 40 is 20. So why bother? Instead, the only equation you have in the x-axis is this one. Whoopsies, this one. That. And you wonder, where did that come from? Well, horizontally, distance is rate times time. If you think about that equation you've known for 1,000 years. You really have, it's part of this equation in the x-axis, but there's no acceleration in the x-axis, and so that's all 0. So it's just the horizontal range equals the horizontal velocity times time. That's the only equation we've ever used in a projectile motion question in the x-axis. And so this is going to be 20 times 1.9, which, let's see, 20, I should be able to do this in my head, but it's a Friday afternoon, I'm tired. So 38, I get 38 meters. Is that what I wrote down over here? Yes. So 38 meters. Okay, so it lands, so this lands 38 meters from the edge of the cliff. Okay. Oh, the rest of this stuff is conceptual, and it is on the final. So how would the time in the air and the range be affected if the mass of the boulder were only half as much, i.e. only 15 kilograms versus 30 kilograms? It's still launched at 20 meters per second from 18 meters. Does mass, remember Galileo's law of falling bodies, is something falling through the air ignoring air resistance? Does mass and weight, do they matter? Do mass and weight matter? No, all right? So the time something takes to fall 18 meters is going to be the same. And if the time is the same and it's launched still 1.9 seconds and it's launched at 20 meters per second, then there is no change. So no matter what you do to the mass, ignoring air resistance, which is not a bad assumption over short distances at low velocities, then ignoring air resistance, mass and weight have no effect no matter what you do to the thing. Lots of folks, if I give you a question where you have a 30 kilogram boulder and a 15 kilogram boulder neck and neck as they go off at the same speed, lots of folks will incorrectly think that they land at different places because, I'm not sure why, but maybe thinking that the heavier one will fall faster. I suppose that's why. But that's not true. Right? They'll be in the air for the same amount of time and land at the same place. And then how would the time in the air and the range be affected if the horizontal launch velocity were half as much as the originally stated velocity? In other words, it's launched into the air from the same height, but that's 10 meters per second as opposed to 20. Does that affect the time in the air if it still falls 18 meters? No, because time is based on the y-axis, and the initial y velocity is still 0. So it doesn't affect the time in the air. It's still going to be 1.9 seconds. Does a change in the launch velocity affect the range? You bet it does. All right? Because the range is that launch velocity, 20, of 10 in this case, because it's going to be half of it, right? In question 18, it's half as much, right? If you have half the launch velocity, you're going to have half the original range. And so that would be 10 times 19, which 1.9, which would be 19 meters. Whatever you do to the launch velocity directly affects the range. So they're directly proportional. They're directly proportional. Whatever you do to the launch velocity directly affects the range. Okay, whatever you do to the launch velocity directly affects the range. You double the velocity, you double the range. You triple the velocity, you triple the range. You cut the velocity in half, as in this question, you cut the range in half. It doesn't affect the time, though. All right, that's the end of that one.